Good evening. Welcome to the event. Can you please rise as we welcome the procession into the venue? Thank you. Thank you. You may be seated.
So good afternoon, everyone. My name is Ingrid Willard, and I'm the Dean of the Faculty of Economic and Management Science. It's my enormous pleasure to welcome you to this inaugural lecture of Professor Rulof Berger. I've got a few special welcomes that I need to do. So beginning with our representative from the Rectorate, Professor Stan du Plessis. Thank you for being here. From our Vice Deans, we have Professor Renel de Priest-Snyman and Professor Pieter van Willig. Special welcome to the Chair of the Economics Department, Professor Ada Janssen. And then, of course, to all the friends and family and colleagues that are in the room. Particularly want to welcome the Rulof's family. So we have, where's everybody sitting? They're hiding at the back. So warm welcome to Ansa and to Rulof and Ansa's 3 children, Emily, Wilhelm, and Annabelle. I did speak to them earlier. At least one of them is thinking of becoming an economist, so this is pleasing to hear. Rulof's parents, Lydia and Connie Berger, that I welcomed earlier. Ansa's dad, Hannes van Wyk, is with us, and his wife, Julian, is online, so a warm welcome to both of you. Some of Rulof's colleagues from Predictive Insights and Elwave are here. A warm welcome to you. Oh, and online we have the legendary Professor Francis Thiel, who was Rulof's PhD supervisor. So we're very glad to also have Francis joining us this afternoon. So an inaugural lecture is an opportunity for a new professor to profess. And so what we mean by that is that we expect him or her to demonstrate something of their work, but in a way that is accessible to a broader audience. So this is a chance for them to speak not only to their peers, and it's lovely to see so many members of the department here, but speak more broadly to the broader society and your community. So Rulof, it is always a tough thing to do. You need to make this accessible. You need to make sure that your mother-in-law can go home this evening and be able to tell her next-door neighbor what you spoke about. That's the challenge. My job is much simpler. My job is just to give you a very brief introduction to Rulof and his career. So Rulof initially studied here at Stellenbosch University. He did a BCom in mathematics, followed by a BCom honors in economics, which he was awarded with distinction. He won the Kuta Medal, a most prized medal in the economics department for the best postgraduate student. And he also won the Finansies and Techniek Prize for Best Honors Student in Economics. Then did an MCom here at Stellenbosch, which he was again awarded with distinction. And he was our contestant in the budget speech competition, which is a competition I think quite a few of us in the room have entered. But Rulof won the competition, which most of us did not. And Rulof went on then to do a master's at Cambridge, and before returning to Stellenbosch in 2000. No, Rulof was appointed at Stellenbosch University, then he went to Cambridge, and then he came back briefly. And in that brief period that he came back, I looked up what was he kind of doing, and he published a couple of papers during that time. One of those papers was with Pierre de Villiers. I don't think Pierre's here. I didn't see him. He published a paper with Pierre about the macroeconomic impact of the HIV/AIDS pandemic. Extremely technical crow paper, okay? And he wrote another paper that year, which he co-published with me, which was about 10 years of labor markets in South Africa post-democracy. And I do think that we might note which of those trajectories he continued on. I don't think he's done a whole lot of macro since 2005. He's done a little bit. He did publish a paper with Stan a year later on the Phillips curve. But it was nice to see these 2005 papers, which were really speaking to highly technical work in the case of the macro paper, and data-driven paper and data-driven work in the case of the labor market paper. And I think that that's something we've just continued to see in Rulof's work. All his work is about great techniques, good data, and having something to say. So it was really nice to see that went back all that way. He then went on to study, to do a DPhil at Oxford, together with Francis Thiel, and then he returned to South Africa and back to Stellenbosch University, and we're very glad that he did that. You had lots of options after the DPhil, but you chose to come back and invest in a career in South Africa and Stellenbosch University. In addition to doing wonderful academic work, Rulof is very committed to doing good commercial work. And so in 2018, he was part of the founding of a company called Predictive Insights, which is a data science company that builds models for companies looking to try and understand human behavior. And so he's managed to find this balance where he is half-time with us and half-time at Predictive Insights, and he gets to do things with data, I think, in both jobs, which is an amazing career to have managed. So Rulof has published widely. He's published on topics such as affirmative action, job search, the fertility transition, teacher pay, migration. So a very, very wide range of work he's done. But as I said earlier, always about great techniques, good data, and remaining relevant. He has publications in top journals such as Health Economics, the Journal of African Economies. He has 2 papers in the American Economic Journal, Applied Economics. So Rulof, this is the pinnacle of an illustrious academic career. We appreciate all the amazing work that you do, both with rigor and relevance, and we look forward to listening to you this evening. Ladies and gentlemen, I give you Professor Rulof Burger.
Thank you, Ingrid, for those kind words of introduction. Can everyone hear me? Good afternoon, everyone. Let me start by acknowledging the Chief Operating Officer, Prof. Stanley Plessis, the Dean of Faculty, Professor Woolard, the Vice Deans, Professor van Wielich and Professor Duprius Neyman, the Head of the Department, Prof. Janssen, colleagues, students, friends, and family. Thank you all for being here. It's a tremendous honor, and if I'm honest, a little bit daunting to give this lecture on the role of economists in the era of machine learning. Before I start the lecture, I'd like to just take a moment. I'd like to just take a moment to express my gratitude to those who played an important role in my academic journey to this point. Firstly, Sir Vaas van den Berg and Stan du Plessis, my mentors in the economics department. Your lectures and research made me realize that I wanted to become an economist, and I still learn from you, so thank you. Thank you also to my doctoral supervisor, Francis Thiel, who's joining us online, and who taught me how to think rigorously about all the things that can go wrong when we analyze data. Then Andri Skumbi, who was head of department for most of my career. Andri, under your management, the department supported me in a way that had a profoundly positive impact on my career. So thank you for that. Thanks also to your successor, Ada Janssen and our Dean Ingrid Woolard, for continuing that support. I also extend my gratitude to my colleagues at the economics department and all my co-authors for the collegial and stimulating working environment, our excellent support staff, past and present, for the miraculous work that you do, my colleagues at Predictive Insights and AlphaWave, where I'm allowed to continue doing research on interesting aspects of human behavior, Jonathan Dale and his team for organizing this event, and then turning to my family, thank you to my in-laws, who some of them are here today, some of them are joining online, for welcoming me into your family. My siblings, Runel and Kobus, there we go, Kobus, who are also my colleagues at the economics department and frequent collaborators. So we may all want to spare thoughts for my poor parents when the conversation at the family dinner table turns to economics. Then thanks also to my parents, Kuni and Lydia, for the loving and nurturing environment in which you raised me. And then last but not least, my wife and children, Ansa, for being so encouraging of my career and for those 4 very long English winters where you waited for me to finish my PhD. Thank you, and sorry again. En dan laastens my kinders, Emily, Willem, Annabel, dankie vir julle ook. Economists are social scientists. We strive to understand human behavior. What is it that economists do? I'm often asked. Well, on the one hand, we've developed economic theories, logically consistent hypotheses for why people behave in the way that they do. Historically, the foundational premise of these theories have been some notion of rationality, that people do not deliberately do things that are detrimental to their own well-being. Over the last few decades, we've increasingly also been able to incorporate insights from psychology and neuroscience to expand the range, the motivations that drive behavior. On the other hand, we've also developed statistical or econometric tools that can deal with the problematic real-world data that we use to test these theories. Combining economic theories and econometric tools have produced and validated economic models that can explain a broad spectrum of behavior, including the existence of financial bubbles, bargaining power between a husband and a wife, the factors that make some countries more vulnerable to civil wars, and even why so many of us buy gym memberships we end up not using. We are living in an exciting time for social scientists who seek to understand the world through data analysis. The advancement and refinement of machine learning methods enabled us to develop more sophisticated and realistic models of behavior. These tools, combined with the exponential growth in computational power, the rapid accumulation of behavioral data, and breakthroughs in neuroscience, are poised to revolutionize our ability to create behavioral models of unprecedented power. By making it easier to turn complex data like text or images or videos into analyzable formats, machine learning has also made it possible to investigate behavior using novel types of information. One prominent example that comes to mind used satellite imagery to pinpoint the precise timing and spatial patterns of smoke emanating from a massive Indonesian wildfire, which provided accurate data of how much air pollution different households in small areas were exposed to. This data was then linked to census data to demonstrate persuasively greater exposure to air pollution caused a substantial increase in infant mortality. Another economist used 1 billion English language tweets to show that our inclination to use profanity is at its lowest at temperatures between 18 and 21 degrees Celsius, but increased noticeably as temperatures either rose or fall. So truly, a broad spectrum of behavior. Although I'm a proponent of expanding the use of machine learning models in social sciences, I do think we need to be realistic about what these methods can achieve. When listening to AI enthusiasts, I suspect, like me, you're often left with the impression that autonomous machine learning and AI, fueled by vast data sets, will soon be able to answer most of the pressing questions in the world, including those about human behavior, and in a way that may make analysts redundant. I think this perspective is wrong. In fact, I believe the role of economists and social scientists is more critical than ever. Machine learning techniques excel at finding nuanced patterns in the data that human analysts will overlook, and under the right conditions, they can produce predictions of behavior that are astonishingly accurate. But these algorithms are vulnerable to data problems that are common when working with data produced by human behavior, like misinterpreting correlations as causation, sample selection bias, or measurement error. Moreover, these tools usually estimate very complicated functional forms that are difficult to interpret and that limits what we can learn about the underlying processes that shape behavior. In today's lecture, I will share examples from my own research that will highlight the vital role of social science theories and domain expertise using data to understand behavior. I will focus on 3 areas where machine learning methods require human ingenuity. Firstly, interpreting data where correlation does not imply causation. correlation. Secondly, handling data affected by sample selection. And thirdly, deciphering the mechanisms of the data. We start with the first topic, which is what economists do when correlation does not imply causation. Data analysts try to find patterns in the data that will help us understand the world. However, correlations in data can often produce misleading narratives and poor decision making. As an example, take a 1999 study published in the prestigious scientific journal Nature. In this paper, medical researchers studied data on nearsightedness in children and found that those who slept with the lights on were 3 times more likely to become nearsighted. The researchers interpreted this statistical correlation as a causal relationship, that sleeping with the lights on caused the children to become nearsighted. The implication was seemingly straightforward. To prevent nearsightedness, children should sleep in the dark. However, soon after, a different group of researchers collected their own data, identified a critical oversight in the initial study. They found that nearsighted parents were more likely to have nearsighted children. In addition, nearsighted parents often left lights on in their children's rooms, presumably to help them see better. These two causal relationships produce a correlation between children who slept with the lights on and subsequent nearsightedness, but the correlation was not causal. The initial study mistakenly attributed a cause and effect relationship to a mere statistical association between 2 variables, a common error in data interpretation. This is one of the problems where machine learning algorithms on their own cannot help us. Although they're excellent at detecting correlational patterns, they can't distinguish between correlation and causation without the help of humans. Economists have developed many tools to help identify causal relationships from existing data, including instrumental variables, panel data methods, regression discontinuity design, difference and difference estimators, and some of my research has applied these methods to existing data to try to find causal effects. For example, in a study with Sefas van der Berg and Dieter van Vintel, we used a series of surveys to investigate the sharp increase in unemployment observed during the 1990s, which at the time caused alarm in policy circles due to the new phenomenon of jobless growth. We found that this was largely caused by an education policy that was implemented to reduce the large number of overage learners in the South African school system. By pushing 900,000 overage learners out of the school system and suddenly into a labor market where they struggled to find work, this policy had caused an increase in the unemployment rate. However, for many questions, the existing data is insufficient to identify causal relationships. In these cases, we need to create new experimental data, preferably through randomized controlled trials, or RCTs. RCTs have long been the gold standard for estimating causal effects and have been used in clinical trials since the 1940s to test the effectiveness of new drugs and vaccines. In these trials, participants are randomly assigned to either a treatment arm who received the drug or a control arm which does not. The drug's effectiveness is then measured by comparing health outcomes between the 2 groups, allowing for a clear assessment of its impact. Randomization ensures that the 2 groups cannot be systematically different, which was the problem with the Nightlight study. The idea to use randomized control trials in economics is comparatively new, where we use it to evaluate the effect of behavioral interventions or policies. And this approach was pioneered by a group of development economists who were awarded a Nobel Prize for their contribution in 2019. So let me explain how we use these methods in economics with another example from my own research on the topic of South African unemployment. In 2011, Martin Abel, Patricia Pereira, and I were curious whether helping young job seekers with some work experience acquire reference letters would be useful for firms and job seekers. Why reference letters? Well, we know that South African employers have a hard time finding young workers with the required skills. When a firm advertises a vacancy in an unskilled or semi-skilled position, they're often swamped with thousands of job applications from interested job seekers, but such applications typically provide very little useful information about the skills employers care about. This is particularly true for soft skills like reliability or work ethic. As a result, most vacancies in this part of the labor market are filled through social networks, where a current employee can vouch for the reliability of a new hire. Unfortunately, this is not an ideal equilibrium. It leaves productive workers with no social networks at a disadvantage, and it means firms need to recruit workers from a smaller pool of candidates, which may exclude the best workers for them. A reference from a previous employer could potentially be highly beneficial in this context, as it reflects an employer's first-hand observation of the job seeker's workplace behavior. The first thing that we did was to gather data on the usage of reference letters among young job seekers with less than tertiary qualifications. We found that such letters were uncommon and typically very uninformative. The few examples we encountered were often letters from school teachers or pastors stating that they knew the candidate, but they failed to mention any skills or even list any contact information. To address this, we designed a new reference letter template which job seekers could ask previous employers to complete. So these are 2 copies of our reference letter template that was completed by the previous employers of 2 of our study participants. As you can see, the template requires that employers provide some personal information, including their contact details, and then circle the relevant skills rating to assess the job seeker's competence in a series of hard and soft skills. Instead of requiring that the employer go to their computer, sit down, and type and print a new reference letter, or we suspect often just change the name at the top of the previous uninformed reference letter that they wrote, they can just grab a pen and complete a short form. Our aim was to make the reference letters simple and quick for employers to complete, which should make them easier to obtain for job seekers. We hope that requiring the employer to assess the applicant in a variety of hard and soft skills would make the letter more informative, and that providing contact and personal details would make it more reliable. Next, we conducted several experiments to understand the effect of reference letters on the job application process. In the first experiment, we asked participants to provide us with all the materials that they typically used when applying for jobs, as well as a completed reference letter. We then scoured the internet for appropriate vacancies to which we applied on behalf of the study participants. In some randomly selected applications, we included the completed reference letter. This experiment taught us 3 important lessons. First, despite being uncommon, reference letters are useful for job seekers. When we applied on behalf of job seekers, randomly including a reference letter led to a 60% increase in interview requests. Secondly, reference letters are also useful for firms. Through skills tests not disclosed to employers, we observed that reference letters helped companies select more skilled workers. The third lesson, which may be of interest to those of you who are asked to write reference letters, is that the content of the reference letter matters. More positive reference letters were generally more beneficial, but a perfect reference letter where the applicant was assessed as being very good at everything was less useful than one that acknowledged a few weaknesses. It seems employers are suspicious of reference letters that are implausibly positive. In a second experiment, we recruited a different group of young job seekers and then provided randomly selected participants with a reference letter and encouraged them to use it in their job applications. We saw that when we gave female participants the reference letter templates, their probability of finding work over the next 3 months increased by 50%. This is a large effect, and it can be achieved from the perspective of policymakers for the cost of a few photocopies. However, we observed no significant effect for males. To understand this discrepancy, we performed a third experiment. We invited job seekers to apply for recently posted vacancies through us, the experimenters, and then we forwarded the application to firms. Through this experiment, we could see that males were much less likely to utilize the reference letter. Not surprisingly then, receiving a reference letter template is of no value to those who choose not to use them. This research was conducted in collaboration with the Department of Labor. Following the completion of the study and the encouraging results, we provided training to their staff on the effective use of the templates, which has now been implemented in multiple provinces. Additionally, we partnered with local NGOs that focus on young people, on helping young people find work, to disseminate these templates to a broader audience of job seekers. For example, Arambe Youth Employment Accelerator recently made the reference letter template accessible to their 1.5 million registered job seekers where they tell us it has become one of their most popular and frequently utilized tools. The second data issue I want to discuss is how economists deal with sample selection bias. When analyzing data, we often rely on statistical tools that assume that our data represents the entire population fairly. However, in the real world, our data often suffers from what we call sample selection bias. This occurs when, for whatever reason, certain observations are either excluded or underrepresented in our data. My experiences of analyzing many different data sets spanning both academia and industry has demonstrated to me just how common this problem can be. Let me give you 3 brief examples to illustrate the nature of this problem. During the COVID lockdowns, the Coronavirus Rapid Mobile Survey, or CRAM, aimed to keep track of how households were doing in terms of key indicators like unemployment, child hunger, and government assistance. Our sampling team had to figure out how to gather a representative sample of South African households, despite the tendency for online and telephone surveys to underrepresent key demographics, such as the elderly, the poor, and rural households. Since these groups were in many ways the most affected by the pandemic, this sort of sample selection bias would have produced an overly optimistic portrayal of household conditions during the lockdown and potentially poor policies. In work with Derek Yu, we investigated what seemed like a 40% decrease in the average earnings of South African workers between 1995 and 2005, which at the time was both worrying and puzzling. We found that this drop was completely explained by changes in the survey questionnaire used since February of 2000, which now included more questions and prompts to ensure that workers in low-wage, informal employment were accurately captured in our data. These changes caused a sudden jump in the number of informally employed workers in our data, and as a result, a sudden drop in the average wage. One of the things that we do at Predictive Insights is to train machine learning algorithms on historical sales data to forecast future sales. But historical sales can occasionally be misleading. In quick service restaurants, for example, we sometimes see surprisingly low sales in certain items due to stockouts. If we do not detect and exclude these data during pre-processing, it can cause our models to learn these patterns and predict similarly low sales in the future. The point of these examples is that we need to guard against becoming this guy, who confidently draws incorrect inferences about the world from a biased sample. In many contexts, sample selection is unavoidable and requires that we think carefully about why it occurs and how it affects our data. Machine learning methods are excellent at discovering and replicating patterns in the training data we provide them, but that means that biased data can produce biased predictions. In fact, many of the well-documented biases in AI, like facial recognition algorithms that perform worse in correctly identifying minorities, or recruiting tools that reveal a bias against women, can be traced back to biases in the samples used to train these algorithms. To explain how economic tools can deal with sample selection, I again used an example from my own research. In 2014, Zoe McLaren approached me with an interesting sample selection problem. She obtained 7 years of data from the National Health Laboratory Services on all patients who had been tested for tuberculosis or TB in public health facilities between 2004 and 2010. At the time, TB was the leading cause of death in South Africa. In this data, we could also see the outcomes for all patients who had been tested for multi-drug resistant TB, or MDR TB, a particularly concerning form of TB that's resistant to 2 primary treatment drugs. Drug-resistant TB is much more expensive to treat and has a substantially higher mortality rate than drug-susceptible TB. It's something we ought to be concerned about and of obvious importance that we monitor how common this strain of TB is in South Africa. Now, in the data, we could see that roughly 13% of TB patients were selected for drug resistance testing, and among this subgroup, 10% tested positive. So that means that 1.3% of all TB cases were clinically diagnosed as being drug resistant. There's a little bit of stats. So personally, I find it easier to think about these things diagrammatically. So suppose the big yellow area represents the South African population. And some of that population, represented by the green circle, have TB. And some people with TB have a specific strain, which is drug-resistant TB, represented by the red circle. For the purpose of this study, we're only interested in the TB-positive population, so we can zoom in. Now, we're interested in knowing how common drug-resistant TB is in South Africa. We'd like to measure this by calculating the prevalence rate of drug-resistant TB. That's the red area expressed as a share of the big green area. The problem is we only know whether or not someone is drug-resistant if they were tested for drug resistance. And most people were not tested for drug resistance. Suppose we represent the tested patients as everyone inside of the dotted circle. We know the drug resistant status of everyone inside the circle, but we don't know the status of anyone outside of the dotted circle. We can reflect our ignorance about the untested patients by hiding the part of the red circle outside of the dotted line, as is the case in our data. The new red area now represents all patients who were tested and who tested positive for drug resistance. In other words, everyone clinically diagnosed with drug-resistant TB. When we express this red area as a share of the big green circle, we get 1.3%. But remember, that's not the same as the prevalence rate, because we don't know the drug-resistant status of all TB patients who were not tested. Hypothetically, it's possible that if we test everyone, we could find no new cases and learn that all drug-resistant cases were already identified by prior tests. It feels more likely that there will be, at least be some cases who are newly identified when we test more patients. And unfortunately, it's also possible that universal testing could reveal that drug resistance is much more common than we had anticipated. All three of these scenarios are consistent with the data that we can see. So, what can we really say about the prevalence of drug resistance with the data we have? Answering this question requires thinking about sample selection bias. The problem is that clinicians do not select patients for testing at random. They specifically target patients they think are likely to be drug resistant based on factors they observe, like previous TB treatments, treatment responses, and risk factors, like HIV status. But these indicators are imperfect predictors, and we don't know how good they are at predicting drug resistance. The key to understanding sample selection bias is to know how accurately clinicians are able to select patients for testing. To help us think about this in a structured way, a thought experiment is useful. So let's explore two extreme scenarios. First, let's assume that clinicians can perfectly identify all drug-resistant patients. In this scenario, the 13% of patients selected for testing would already include all drug-resistant cases in the country. Testing more patients wouldn't uncover any new cases. In this situation, the population prevalence of drug resistance would be precisely 1.3%. Now consider the opposite extreme. Clinicians are completely ineffective in their selections. In this case, the patients for testing represent a random or haphazard sample from the population, and we know that among the 13% tested, 10% were drug resistant. If clinicians had selected these patients at random, that means that if they test another 13%, they would again find a 10% drug resistance rate. This suggests a population prevalence rate of 10%, not 1.3%. And you don't need to be a public health expert to understand that whether the true prevalence is 1.3% or as high as 10% makes a real difference for how we think about allocating resources to this problem. In reality, clinicians are unlikely to be either perfect or completely ineffective at selecting patients. The truth is probably somewhere in between those two extremes. That means that the prevalence rate must be somewhere between 1.3 and 10%. Again, hypothetically, with enough time and money, we could increase the number of patients who are tested and observe how many new cases are discovered. If very few new cases are found, this would mean that clinicians are very good at selecting patients for testing, and the prevalence rate would only be slightly higher than 1.3. If, on the other hand, we discover many new cases when we increase testing, that implies that selecting the right patients for testing is difficult, and the prevalence rate may be closer to 10%. Now, we can't we can't actually test more patients, but we can look for what economists call natural experiments. In this case, instances where coincidental factors conspired to cause a change in the testing share that acts like an experiment. For example, in 2006, a conference presentation in Denver on a new strain of extensively drug-resistant TB raised concerns about drug resistance in the medical community and caused a sudden increase in drug resistance testing in South Africa. We can use these jumps in testing to see how many new cases were discovered, which allows us to identify how good clinicians are at choosing patients for testing, and by implication, how many undiagnosed cases are out there. So what we did was to formulate a simple economic model in which clinicians try to select drug-resistant patients for testing, but are informationally constrained in how well they can do this. We then estimated the two parameters of this model, the unknown prevalence rate and how easy it is to identify drug-resistant patients. Our model found that the drug-resistant TB prevalence rate that best explains the patterns in our data was 3.0%. Now, if this were true, it would imply that more than one-half of drug-resistant cases were undiagnosed by clinical tests in the period that we considered. It would also suggest that the WHO's prevalence rate estimate at the time underestimated drug resistance by nearly 20%. In 2017, the same year our paper was published, the first ever national TB prevalence survey was launched in South Africa. 50,000 randomly sampled individuals were tested for TB, and if they tested positive, also for drug resistance. These surveys are expensive, they're invasive, and they take very long to complete, which is why they don't occur more frequently. But crucially, this would be the first time that we could obtain an estimate of the drug resistance prevalence rate from a nationally representative survey that wasn't affected by sample selection bias. The results, which were released in 2021, 4 years after our study, found an MDR prevalence rate of 3.1%, which is very close to our estimate of 3%. I should add that the issue of monitoring drug resistance is less important in South Africa these days. Universal testing for drug resistance has since been implemented, and TB is no longer the leading cause of death in South Africa. But still, I hope this example demonstrates that even when the data is severely skewed by sample selection bias, a sensible model that explicitly considers the nature of sample selection can provide reliable answers to very important questions. The last topic I want to discuss is how economists study the underlying mechanisms of behavior. That is, the deep-rooted processes or motivations that operate beneath the surface to produce observable behavior and outcomes. One research topic that I've often worked on is discrimination. Along with Rachel Jafta, Dieter van Vintel, and Reit for the Black, I've written a few papers and book chapters that track the wage gap between white and black South African workers during the years of affirmative action policies. These investigations usually find that this gap has remained relatively stable since political transition, except perhaps for a narrowing at the very top of the skills distribution. However, as was the case for nightlights and reference letters, if we want to estimate the effect of discrimination, we need data gathered from experiments. One example of such an experiment is a recent study where researchers submitted 80,000 fictitious job applications to large American companies. These applications were identical in terms of work history and skills, but the names were randomly assigned to be either distinctively white, like Greg or Emily, or distinctively black, like Jamil or Lakeisha. By analyzing callback rates for different names, researchers can gauge the labor market penalty of a distinctively black name, shedding light on hiring discrimination. The study found that presumed white candidates were contacted 9.5% more often than presumed black candidates. One question that's not answered by these studies is what happens in the brains of hiring managers when they decide to call back white but not black applicants. Neuroscientists have identified two functionally distinct cognitive processes that occur in our brains. System 1 operates instinctively, and System 2 is deliberate and analytical. To illustrate how they differ, consider this image of a man. You can immediately tell that this man is angry, right? You don't need to think about it. That's because humans have evolved to recognize anger and the threat of danger instinctively. This is an example of system 1 at work. Apart from being quick, this system is also involuntary. You cannot look at this picture without also noticing that the man is angry. That's because system 1 doesn't have an off switch. This cognitive process also occurs at a subconscious level. So we cannot, through introspection, unpack which aspects of this picture are most responsible for the cascade of associations that it triggers. On the other hand, if you look at this picture, you can tell pretty quickly that it's an unsolved equation, but you will not solve it instinctively. Solving it requires making a conscious effort to activate system 2. Unlike system 1, its activation is voluntary. If you decide to activate it, your heart rate will increase slightly, your pupils will dilate, and you will very gradually begin to burn calories. That's because system 2 is slow and effortful. Very slowly, I should add. System 2 also works at a conscious level. That means when you start solving this equation, you'll be aware and able to guide your thought process. Returning to the issue of discrimination, a fundamental question now arises. Which system, system 1 or system 2, is primarily responsible for hiring bias? Is discrimination caused by negative stereotypes that we unconsciously associate with certain races and that guide our subsequent decisions involuntarily? Or is it the result of beliefs that reside within our prefrontal cortices, where we are fully aware of them and where they have withstood conscious scrutiny? To answer this question, Martin Abel and I conducted an online experiment on US residents. That's residents in the United States of America, not the University of Stellenbosch. I should make that clear. We began with a data set from a prior study that measured the productivity of workers with different races and first names in a transcription task. From this data set, we selected names that were distinctively black, distinctively white, or clearly ambiguous. Participants in our experiment were then presented with a selection of these names and asked to report the perceived likelihood that each name belonged to someone who is white or black. For each name, we also asked them to predict the value of various attributes, like years of education and the productivity in our transcription task. Finally, we presented participants with pairs of names, like Greg versus Lakeisha, and instructed them to hire the more productive worker. In 1/3 of cases, participants were required to make this decision quickly, within 2 seconds, while in the remainder, they could take as much time as they wanted. All of these tasks were incentivized, meaning participants received monetary rewards for answers that were closer to the truth. Our analysis of the data found that employers usually hire the candidate that they previously predicted to be more productive, which is what we would expect to see. However, about 30% of hiring decisions diverge from this pattern, with employers choosing the less productive candidate. In a significant majority of these cases, the preference leaned towards candidates perceived as more likely white, especially when employers were put under time pressure. One potential explanation for this behavior is that employers use multiple cognitive processes when making hiring decisions. When considering a name, system 1 may quickly trigger associations related to the candidate's race, but as thinking time continues, the employer may update their beliefs away from System 1's initial assessment as System 2 introduces other, more relevant attributes, such as predicted productivity. To test this hypothesis, we applied a model from neurophysiology called the drift diffusion model to our data. The drift diffusion model has been validated as accurately describing what happens in our brains when we make binary decisions, like choosing between a pizza and a hamburger at a restaurant. This process entails eliciting relevant associations from memory to start accumulating evidence that one option will produce a more preferred outcome than the other. When that evidence that your brain is calculating reaches a decision threshold, a choice is made. The model predicts, amongst other things, that decisions should be quick when one option is clearly preferred to another, and slower when the two options are closely matched. It has demonstrated an uncanny ability to explain the joint distribution of choices and decision times in an experimental setting, And when people are subjected to brain scans during decision making, the activation of brain regions support the hypothesized working of the drift diffusion model. It therefore appears to be a good representation of the neurobiological processes that occur during simple binary decisions. When we apply this model to our data, we find that it can successfully explain many of the observed patterns that we see. For example, we find decisions are made swiftly when one candidate is perceived as more productive and more likely white. In contrast, if one candidate is viewed as more productive and more likely black, this results in slower decision making. Our estimates indicate that for the group as a whole, much of racial discrimination occurs in the first few seconds of decision time, seemingly because System 1 quickly triggers negative subconscious associations for names perceived to be black. Once System 2 takes over and employers consider the choice more deliberately, decisions become less discriminatory. This suggests a shift in attention during the hiring decision, where easily accessible race perceptions are initially important, but attention eventually shifts towards more relevant attributes. The results imply an important role for System 2 to supervise the knee-jerk associations of hiring managers and to correct negative stereotypes. It also suggests that rushed decision-making, which is common when employers work through large stacks of applications to arrive at a short list of candidates, is particularly harmful for black applicants. The apparent importance of System 1, which you'll remember is involuntary and unavailable for conscious introspection, is worrying, since it means that many hiring managers may not be aware of their biases. Next, we decided to investigate whether there are any interesting differences between employer subgroups. Our model predicts that time pressure should only affect the decision of employers for whom there's an inconsistency between their quick System 1 associations and their conscious System 2 beliefs. To test this, we divide our participants into three subgroups. Black employers, who we believed would be least vulnerable to negative System 1 responses to black names. White employers, who strongly oppose affirmative action policies, which other studies in the US have identified as often associated with racial resentment, and we may therefore harbor negative System 2 beliefs about the productivity of black workers, and white employers who support affirmative action policies. We find that black employers exhibited only a small negative System 1 bias against black names, and this produced a similarly small degree of discrimination in both quick and slow decisions. White employers who strongly oppose affirmative action policies, on the other hand, displayed a large negative System 1 bias against black names, which persisted in slower decisions. This suggests that the negative System 1 response was endorsed rather than corrected by System 2. In contrast, white employers who support affirmative action revealed the largest divergence between quick and slow decisions. In quick decisions, they revealed nearly as much discrimination as white employers who oppose affirmative action, indicating a similarly strong System 1 bias against black candidates. However, in slower decision, most of this discrimination was reversed, suggesting an active role for System 2 in policing and correcting the negative associations of System 1 when given the time to do so. In a different study, we may have decided to train machine learning algorithms on our data to accurately predict which workers will be hired by which kind of employers, or to find interesting patterns in the data. But achieving the objective of this study, which was to untangle the underlying mechanism that produces discrimination, and ideally in a way that mimics the working of the brain, required applying insights from social and neuroscience. In conclusion, the era of machine learning presents exciting opportunities for economists and social scientists seeking to understand human behavior. They will help us uncover nuanced and surprising patterns in the data, prompting new questions and development of more refined theories. They will improve our ability to forecast behavior more accurately and they will unearth more interesting data that we can use to test our theories in novel ways. However, it's important to recognize that machine learning techniques will not solve many of the data challenges faced by social scientists. Like traditional statistical methods, they can mistakenly interpret correlation as causation and are prone to sample selection biases. Addressing these concerns requires domain expertise to determine whether specialized statistical methods, different analytical models, or improved data are necessary. Moreover, to fully understand the underlying mechanisms of behavior, an interdisciplinary approach that integrates insights from social sciences such as economics, psychology, and neuroscience with robust statistical methods is essential. By harnessing our theoretical and methodological expertise, we can continue to generate valuable insights into behavior and address significant statistical issues. Thank you.
Good evening, ladies and gentlemen. Science, and social science also, is a cumulative activity. We build on the work of those who have come before us, and those of us who have had the privilege to travel as economists here in Stellenbosch are excited to see the ambition and the accomplishment of a new professor such as Rulof Burger. It is thrilling to listen to him, and we are proud of our association with such a scholar. As economists, we have come a long way since our dear master Adam Smith showed us the first understanding of human behavior in our discipline. Even he based his views on what would now count as very little evidence. A bag full of philosophical prejudice, enlightened though they were at the time, and then a pretty dogmatic view of the role of special interests in government. It is sobering to remind ourselves that he thought even worse about the management of universities. Now, if I take the story a century forward from Adam Smith to the great Jevons, much was already better in our science, in the sense of incorporating empirical evidence in public policy reasoning and in economic reasoning in general. In fact, he announced very helpfully that we cannot really plan out social reforms based on theoretical grounds. It would have been even better if that was what he precisely proceeded to do. Another century forward, and the first Nobel Prize was awarded to Ragnar Frisch and Jan Tinbergen in 1969, precisely for bringing together theoretical economics and empirical analysis in the emerging science of econometrics. But even those brave pioneers we now know with the benefit of hindsight were laboring to some significant extent in a dead end. The good news, ladies and gentlemen, is that the last 50 years, since Tinbergen, especially the last quarter of a century, in that period economists have made real progress. Professor Burger has showed us this evening how his work brings together powerful forces to create more sophisticated and realistic theories of human conduct, which promise to revolutionize our ability to create behavioral modes of unprecedented power. What are these forces that he harnessed to such great effect? First, he starts, like Adam Smith, with a strong assumption of rationality. He is an economist after all, and a very good one. And as Gary Becker observed in his Nobel acceptance lecture, this assumption underpins and unifies our approach not just for economics, but indeed for social sciences more broadly. With the economic theory built on this core assumption, he adds powerful statistical tools, and he deploys these with great insight. He uses the exponential growth in computational power, the rapid accumulation of behavioral data, and breakthroughs in neuroscience and psychology. While this work is firstly and primarily anchored in the economic tradition, his research also shows the power of interdisciplinary work, as we see with many of the most promising research programs in the university today. In fact, when you listen to the lecture, you can see that it must really be tremendous fun to work with Rulof. He also showed us with striking examples from his own work that the scientist, the economist in his exemplary case, does not disappear behind all of that data and all of that machine learning. On the contrary, without the experienced economist, even these powerful techniques are open to biases such as sample selection, endogeneity, and measurement theory. But together with these powerful tools, we need the theoretical mastery. You have to be a very good economist and domain expertise, as Rulof calls it. That is, you need to understand the data and the social circumstances within which it emerged. And his examples of this are really very striking. In the labor market, he showed us some of the dangers of discrimination, but also how you can help with the job prospects for young South Africans in reference letters. He showed us work on family income in household surveys. And then that tremendous study in which he used excellent technique and insight in sample selection bias to predict with tremendous accuracy the rate of multiple drug-resistant TB in our population. Now, very few of us as scholars will ever have the privilege to precede a large survey by more than 10 years on a significant number such as a 50% underestimation of an important social event. When Keynes wrote about economics or the economic contributions of his friend, late Frank Ramsey, a century ago, he referred to the delightful paths of our most agreeable branch of the moral sciences, that is economics that he was talking about, in which theory and fact, intuitive imagination and practical judgment are blended in a manner comfortable for the human intellect. These were aspirational sentiments when Keynes wrote them, but this evening we have seen them realized in Professor Burger's lecture, as he showed us how he blends theory and fact, intuitive imagination and practical judgment in a manner that is at least comfortable to his intellect. Rulof, amongst the many joys of 25 years in the economics department, none for me stand above the pleasure of seeing your development from a brilliant student to an inspirational professor. You do us a great honor with your work in the department and as an academic leader within the Senate of this university. As an inaugural lecture should do, yours made us look upwards with eager anticipation for the intellectual life of this department and this faculty and this university. Thank you and congratulations.
Good evening, everyone. It remains for me to end the ceremony, and I'd like to first start off. It gives me great pleasure to extend a word of thanks on this momentous occasion, the inaugural lecture of Professor Rulof Burger. First and foremost, I would like to express my sincere appreciation to Rulof for delivering and enlightening a thought-provoking inaugural lecture. Your expertise, your passion, and commitment to advancing knowledge in the field of data science have set the tone for the academic journey ahead. In this digital age, data is being generated at an unprecedented pace, from the click of the mouse to the swipe of a card, from sensors in our smartphones to satellites orbiting the Earth. This deluge of data presents both a challenge and an opportunity. So the challenge lies in making sense of this vast amount of information, while the opportunity lies in extracting valuable insights to drive innovation, efficiency, and progress. From an economic perspective, data science and machine learning are reshaping the way businesses operate, create new opportunities for growth, efficiency, and competitiveness. And as Rulof's lecture has alluded to, it provides us with models to understand model or human behavior. But as importantly as shown by Rulof, it also illustrates the important role of the economists in understanding this data, analyzing it, and also pinpointing the shortcomings that we can sort of illustrate in the data patterns that is observed. It is precisely this academic offering that Rulof brings to the department and to the students that enthuses our students to choose the degree programs and the modules that he offers. And so Rulof has been and remains an instrumental staff member in strengthening the department's undergraduate and postgraduate academic offering. And through his own research and expanded international research networks, he ensures that we stay abreast of developments on the data side, on the BDAT science program, and ensuring that we have curriculum development that is at the forefront to send our students off and to really achieve the most excellent academic achievements. Despite his busy schedule, Rulof always impresses me with his dedication to the discipline and his sincere devotion to our students and our department. He's an excellent scholar. He's an excellent lecturer, as you've all noticed this evening and have experienced, and he's a friendly and supportive colleague. So I would like to acknowledge the presence of Rulof's family, his friends, his colleagues, and I'd like you to thank you to being here and supporting Rulof in this momentous occasion. Your support and participation have added prestige to this evening. And I'd like to invite all of you to join us in celebrating this wonderful evening with Rulof. Thank you, Rulof.
Please stand. Please stand as the procession leaves the venue. Thank you.